Hi class, this is a partial solution to the problem set that you guys just did. So I just wanted to talk about certain concepts so you are ready for the upcoming application for that. Um, Notice here, this was a question that was given to you. I have here an electrophile, a nucleophile. So first thing, when you look at a problem, irrespective of whether you have learned how to solve that particular mechanism or not, is look for where the electrophile is and where the nucleophile is. So hopefully you can see that the nucleophiles are going to be the lone pair of electrons on oxygen, because that's a somewhat electron-rich center. And if you compare that to the carbonyl, oxygen being more electronegative is going to pull the electrons towards itself, slightly being negative, and that would render the carbon slightly positive, and so that makes it more electrophilic. Now, like I discussed in class, if you have two neutral species, one is behaving as an electrophile, the other behaving as a nucleophile, you pretty much are not going to see a great amount of reactivity, and you will have to increase the reactivity by incorporating either acidic conditions, which are going to increase the electrophilic character there, or basic conditions, which will improve the nucleophilic character there. So one way or the other, you would have a better reaction. So either acid catalyzed, which will improve the electrophile, or base catalyzed, which will improve the nucleophile, is the way to go. So how do we go about this? You should first notice that since this is delta negative, that basically will pick up this proton, and you're going to see a protonated carbonyl. So sometimes some people like to use the pi system. Some people like to use the lone pair of electrons, in which case you will have to show this positive charge on oxygen, which then is going to give you the positive charge on the carbon. If you would have used the pi electrons, then you can just simply place the OH and the positive charge directly, so this intermediate will be generated directly. Anyway, now the alcohol is going to attack, and so you will first see the formation of OH, O, 2 carbons, and then an OH, proton still intact. Now realize that you have an oxygen with a positive charge, and then another OH next door, which is right now neutral, and it is so close that it can actually simply pull that proton off that oxygen. In that sense, it's going to generate the species. OH2 is going to want to leave. It's a tertiary, or rather secondary, with an oxygen right next door. So I'm going to give it that positive charge. And now you can ring close, or close the ring. Still has that proton, and the incoming, since water had left, that can pick up that proton, and you get your product. Realize that this water always will be mixed with a proton, so hydronium ion, it's okay to have that. All right. Another question, which I believe is a very interesting question, and it's similar to, of course, it was a sugar. I'm showing you a cyclohexane here, but idea here is same. You were given a substrate which is being treated with methanol with an acid, in presence of an acid, and you basically are converting this OH into the OCH3. And then two pathways were provided. So one was in which this OH simply attacks a protonated. So what they're saying is that the CH3OH with the proton will form the oxonium species, the OH2 with a positive charge. And as that's leaving, essentially, this is going to attack this methyl, and it's going to do that in a more, hopefully you can see that, SN2 like manner. As one bond breaks, the other gets formed. So at no point of time would you see a stable carbocation, because this is a primary carbocation. The other path that was suggested was that it's not the OH of the alcohol, but rather the sugar, because sugar has a boatload of OHs. That's the one that will get protonated. It would leave behind a carbocation, which here is a secondary carbocation right next to this oxygen as well. So hopefully you can see that that should be able to stabilize that carbocation. And now the alcohol is going to attack, the lone pair is going to attack, get the positive charge, loss of proton, give you the product. And the question was, well, which one of them is more plausible? And the answer goes back to the reaction conditions. Notice we have a protic solvent, we have methanol, which is a weak nucleophile, so all of that is pointing towards SN1. And what is characterized by SN1? Yes, the intermediate should be more stable carbocation. So path B is the one which is a more plausible reaction. And that's about it. That's all that you had to know. Another question was to basically select which one of the two pathways was a better pathway. And I'm not showing you both the options here, but rather how to go about it. And so recall from your class organic 1 that the source of electron is going to hit the slightly positive hydrogen, and Cl is going to leave, and that will give you essentially a hydrogen with a positive charge. That's your tertiary carbocation. And the other option is that you could get essentially a primary carbocation, and hopefully you can see that the tertiary is more stable. Now in this process, what one really needs to see, what one really needs to highlight is that electrons always travel from the source of electron to the sink of electron. So once that Cl leaves, so as the Cl leaves, the proton which is left behind is going to be in dearth of electrons, and since it does not contain electrons, that cannot possibly attack. So you can't show this H plus and the arrow movement towards the double bond. That's a wrong arrow right there. So if you chose that particular mechanism, that's not accurate. Please keep that in mind. Electrons always move from source to sink. There was a question for a what's wrong with this analysis type question, and you were given that there is a hydroxide which essentially is attacking here. And hopefully you can see that as the attack is being shown, basically the carbon sort of is forming a new bond, and it gave you a hypervalent carbon. You basically have 5 bonds on that carbon in the middle, and that is not allowed. Carbon is supposed to be tetravalent, always was, always will be tetravalent. And so if you're showing an attack on that electrophilic carbon, this pi system, which is the most mobile electron, has to move, and so that arrow was missing. So you should draw the structure as a negative charge on oxygen with the methyl and a new OH over here. So this should be the correct structure. Okay, again, the question was that you had to look for what was wrong with this mechanism, and there's more than one things that are wrong. First things first, all your reactions, irrespective of whether they're organic or inorganic in nature, must conserve atoms or matter in general. So notice here you have 1 carbon, 2 carbon, and the 3rd carbon. On the product side, you have 1, 2, 3, and there's 1 that got lost. So total you have 4 carbon atoms, and so you can't create matter at any given point of time. The other thing that you have to keep in mind is that these are acidic conditions. And what did I tell you? Acidic conditions will not allow any negative charge. And here our leaving group is oxygen with a negative charge, which is not something that would be allowed. So when you have to show this mechanism, what I'm about to write is the proper way of going about it. So you would say that you have an oxygen which has lone pair of electrons, and you have the hydronium ion which is right next door, and so the lone pair of electrons will pick up the hydrogen, let that water go, and so that will give you a protonated ester. Now that's going to pull the electrons towards itself, which is why the water is going to attack. You're going to see a positive charge which will be lost to another molecule of water. So yes, your first structure is right over here, and now it first should show a transfer of proton, or just use the hydronium ion, so that your leaving group is not going to be, and I'm going to write that as H3O plus expanded, so that it becomes now a neutral leaving group. And so when the lone pair of electrons kick back in, the methanol is the leaving group, not the methoxide ion. So be careful with the fact that if you have an acidic solution, you cannot have negatively charged species or intermediates in there. And the last what's wrong with me problem was this. So you had to determine what was wrong. And the arrow that was shown was the electrons moving like this, and this proton basically getting here. And hopefully you can see this is a pretty straightforward question. The negative is the source of electron. That's going to pick up the proton, and then the electrons will move. So realize that electrons have to always move in one specific direction. And if you can do that, you probably will have the correct mechanism. All right, see you in class.